class, in this video we're going to be talking about section 2.1, the coordinate plane. And so if you remember from our section on inequalities, a number line is helpful if we need to locate just a single point or a range of values. So number line is useful for locating a single number or a range. Right? So if we had something like this, we could locate if 0 is here, we knew that 2 would then be over here, or if we had less than -1, it's over here, right? So if x equals 2, we have just this point, or x is less than -1, we have that part over there. But what if we need to locate pairs of numbers? So imagine that we start with our number line. Looks like this, right? And our positive is over here, and our negative is over here. And we can place our 0 right there. Well, if I were to take a second copy of this number line, and I'm going to rotate it, and put it here. When we rotate it, the positive comes up here, and the negative comes over here. This is called the coordinate plane. The coordinate plane is just two number lines that are perpendicular to each other. So perpendicular, if we've had a geometry class, we put this little square bracket, which means that they're perpendicular. And we have some names for these things. This first number line we call the x-axis. And our second number line we call the y-axis. So our horizontal number line is our x-axis, and our vertical number line is our y-axis. So this coordinate plane helps us locate pairs of numbers. And pairs of numbers are called ordered pairs. And the reason we use ordered pairs is because suppose I have a coordinate plane, and I say plot the pair of numbers 1, 2. Well, how do I know if that's over 1 up 2 or up 1 over 2? So which one? So mathematicians have agreed upon a convention. And that convention is, in an ordered pair, the first value is the x-coordinate, and the second value is the y-coordinate. So 1, 2, hoping you can't see that. So 1, 2 is our x coordinate, and 2 is our y coordinate. Which means if I draw another set of axes, and if you want, you can write your x and y, just so I know which way it's oriented. And our x coordinate is 1, so on our x number line we find the 1, and our y coordinate is our vertical, so we have 1, 2. We know that this point corresponds to 1, 2, because we have the x and y. And so by convention, that first term, and that's why it's called an ordered pair because we have an agreed upon order of these terms. We always put the x-coordinate first, and we always put the y-coordinate first. And I want to point out that when we're looking at an ordered pair, this looks kind of similar to if we had, say, up here on our number line, -1, 2, right? If we wanted to mark this point between -1 and 2, if we wanted to denote that range, we would write it that way. So it's important that we know whether we're talking about an inequality or we're talking about an ordered pair. And so to keep things simple, when we're talking about ordered pairs, we're only going to be talking about ordered pairs. And we won't be moving back and forth because it has the same notation. So let's talk about maybe plotting some of these points. So I'm going to give you a decently large coordinate plane. X, Y. I always put those arrows because they don't end at any of those points. And we have some examples. So I'm just going to write them all here, plotting the point 2, 2, -1, 0, 3, 0, 0, 4, -3, 1, 0, 0, -4, -1, and 0, -1. Now you might pause and kind of practice plotting each of those points, but then we'll go through them in turn, remembering that our first term is our x-coordinate and our second is our y. So x2, y2 is 1, 2, 1, 2. That's my point, 2, 2. -1, 0. X is -1. Y is 0. -1, 0. 3, 0. 1, 2, 3 on the x, 0 on the y. 3, 0. X equals 0, y equals 4. 0, 1, 2, 3, 4. Here we have 0, 4. -3, 1. X is -3. Y is 1. -3, 1. And then we have 0, 0. So that's this point where the two axes meet. And now this point in the middle has a special term, or a special name. 0, 0 is the origin. So wherever that point is, where the two number lines meet, where both x and y are 0, we call that the origin. -4, 0. X is -4. 1, 2, 3, 4. Oh, and it's -4, -1. So here we have -4, -1, and then 0, -1. And so there we were able to plot those points. And so based on that, we noticed some things. Whenever we're on the y-axis, here x was 0, and here x was 0. So x is equal to 0 whenever we're on the y-axis. And if we're on the x-axis, we had 3, 0, and -1, 0. Our y-coordinate will always be 0. If we're up here, our x is going to be positive, and our y will also be positive. If we're over here, our x is negative, but our y is still positive. So we have negative, positive. Down here, we have x is negative, and y is negative, so negative, negative. And down here, we have positive, negative, positive, negative. And so the coordinate plane is kind of intuitively or naturally is broken down into these 4 pieces. And this is called the quadrant 1, the first quadrant, which generally speaking I'll write as Q1. Here we have Q2, or the second quadrant, Q3, or the third quadrant, and over here we have Q4, or the fourth quadrant. And again, you're like, well, why did I go 1, 2, 3, 4? Convention is that we number our quadrants counterclockwise or anti-clockwise. So there's no reason that it couldn't have gone 1, 2, 3, 4, other than it doesn't. And by convention, mathematicians call this quadrant 1, quadrant 2, quadrant 3, and quadrant 4. And so if we look at the quadrant, sine of x and sine of y, we have 1, 2, 3, 4. In our first quadrant, x is positive and y is positive. In our second quadrant, x is negative and y is positive. Our third quadrant, they're both negative. And in our last quadrant, we have positive, negative. And so those are properties that are always true. When we're plotting them, we end up with our positive and negative values. Jasper wants to join in on the math. Clear him a space. And so we have our 4 quadrants, numbered counterclockwise, starting at the x-axis. Quadrant 1, where they're both positive. Quadrant 2, where our x is negative, but our y is positive. Quadrant 3, where both x and y are negative. And quadrant 4, where x is positive and y is negative. And so that's just kind of basic like orientation to the coordinate plane. And you can remember that these are quadrants because quad means 4, like a quadrilateral has 4 sides. But let's talk about distance. If I have a number line between these 2 points, say -1 and 4, the distance is just my right term minus my left, right? So the number of units between them is 4 minus -1, or 5. There are 5 units between these 2. But if we're in a coordinate plane, is distance as straightforward? So let me draw, and I'm going to draw kind of an abbreviated coordinate plane. And I say, what's the distance between one, 1, and 4, 3? Well, first we'll plot it. So we have x and y, 1, 1, and 4, 3, 1, 2, 3, 4, 1, 2, 3. So that's my points 4, 4, 1, 3. And we want to know that distance. What is that distance? Well, I mean, if we looked at just this distance, we know that that's 3, right? Because from 4 to 1 is 3 units. Or if we look at the vertical distance, we have 1 up to 3, which is 2 units. So how do we find that diagonal distance? And this is where I'm going to remind you of something you may have heard once upon a time. The Pythagorean theorem. Pythagorean theorem. If A and B are side lengths and C is the length of the hypotenuse, of a right triangle, then a squared plus b squared equals c squared. So, since our x is always our horizontal distance and y is always vertical, and we already decided that those two axes were perpendicular by their definition, this vertical distance and this horizontal distance are perpendicular to each other. And that means we can use the Pythagorean theorem to find the length of this diagonal. So like I said, up here we can call this horizontal distance of 3 our A, and our vertical distance of 2 we can call B. So what we have is 3 squared plus 2 squared equals that unknown length C squared. So 3 squared is 9, 2 squared is 4, C squared. 9 plus 4 is 13 equals C squared. And that means that C is plus or minus the square root of 13. So remember, when we take our square root, we get a plus or a minus. But it doesn't really make sense to say that something is a negative length from somewhere else. And so by convention, we'll only use the positive distance. So the distance between this point and this point is the square root of 13, and we'll only care about the square root. So whenever you're finding the distance between 2 points, you plot them, you find their x distance, their y distance, and then we use the Pythagorean theorem to find the distance between them. Now what if I want to know, just like generally, between any 2 points? Suppose I have a point, x1, y1, and x2, y2. So that's just our first point's x value and our first point y value, second point x, and second point y. So wherever they are, x1, y1, and x2, y2, we know that that horizontal distance is x2 minus x1, and we know that that vertical distance is y2 minus y1. And so by our Pythagorean theorem, we know that x2 minus x1 squared plus y2 minus y1 squared is that length we care about. We'll call it L squared. And we can take our square root, and we get x2 minus x1 squared plus y2 minus y1 squared. And this equation, because it has an equal sign, is called the distance formula. because for any point, x1, y1, and x2, y2, so any 2 points, the distance between them is given by this. You might say, well, how do you know which one's x2 and which one is x1? Well, it doesn't matter. As long as, if you have, say, and we can look at our previous example, we had the points 1, 1 and 4, 3. So call this x1, y1, x2, y2. What we end up getting as L is the square root of 4 minus 1 squared plus 3 minus 1 squared. But what if instead you were like, well, I'm going to call 1, 1, x2, y2, and I'm going to call 4, 3, x1, y1. Here what we get is the square root of 1 minus 4 squared plus 1 minus 3. And so let's simplify each of these. So here we get the square root of 4 minus 1 is 3 squared, plus 3 minus 1 is 2 squared, 9 plus 4, square root of 13. So it still works. But if we do this one with the square root of 1 minus 4, which is negative 3 squared, plus 1 minus 3 is negative 2 squared. Negative 3 squared is 9, plus negative 2 squared is 4. We still get the square root of 13. So it doesn't, sorry, there was a moth that just flew by, and it totally caught me off guard. Sure, that's a beautiful look of sheer terror on my face. Our length is the square root of 13. So it doesn't matter which point is point 1 and which one is point 2, as long as x1 and y1 are the same point, and x2 and y2 are from the same point. I can't say do x1, y2, x2, y1. Like I can't switch what they're partnered with. x1 and y1 just means both x and y values are from the same point, and x2, y2, both values are from the other point. But which one doesn't matter. And so that's our distance formula. If you can't remember it, you can always go back and just draw the given triangle and then use the Pythagorean theorem. But the distance formula is kind of the general case that works always. And just because we can use the same example over and over, if I have my points 1, 1 and 4, 3, so 1, 2, 3, 4, 2, 3, 4, 3. What point is halfway between 1, 1 and 4, 3? And that point halfway between is called the midpoint between 1, 1 and 4, 3. And so if we look at this side, and I'm going to draw the rectangle in, and this is our point between them. We want to know, where is that point? Well, that point is halfway between the x values and halfway between the y values. So halfway between 1 over here and 4 is where? Well, it's going to be whatever that distance is, so distance. So to our x distance, which is 4 minus 1, or 3. Well, it's going to just be my starting distance plus half of it. So half of my x distance is 1.5. And so this point is, so the midpoint x coordinate is 1 plus 1.5, 2.5. And then our y coordinate, so our y distance, is 2. So half that y distance is 1. And midpoint y value is our starting y value, 1, plus whatever that half distance is, 1 plus 1, or 2. So the midpoint is 2.5, 2. And notice if I go over 1, 2.5, that's where that is. If I go up 1, 2, that's where that is. And so just like we had a general form that we called the distance formula, we have a general form that's called the midpoint formula. Midpoint formula. We started with our, so if I have x1, x2, nope, x1, y1, x2, y2. I'm going to rewrite that because that's messy. x1, y1, x2, y2. Its midpoint is x1 plus half the distance between them. x2 minus x1 over 2. And its y value is y1 plus half the distance between the y's, y2 minus y1 over 2. I'm going to put that in parentheses because that's our x value and our y value. But this will simplify a little bit. If we get a common denominator of 2, we have 2x1 plus x2 minus x1. Now all over 2. y1, but common denominator of 2, we have 2y1 plus y2 minus y1 over 2, which is the same as, if I have 2 x1s and I take 1 away, I have x1 plus x2 over 2, and y1 plus y2 over 2. And this is our midpoint formula. But notice, when I did my midpoint was my value plus half of the distance, so I had 1 plus 1.5, this tells us that I don't have to find that half distance. It says I can add my two terms together and divide by 2. So if I apply the midpoint formula, I have 1 plus 4 over 2, 1 plus 3 over 2. 1 plus 4 is 5 divided by 2. 1 plus 3 is 4 divided by 2 is 2. 5 divided by 2, 2.52. That's exactly what we said. So it turns out that this, the sum of two numbers and dividing them by 2, is their average. So the midpoint occurs at the average of the x values and average of the y values. So you have a number of things you can remember for midpoint formula. You can either use the point plus half distance for each, or the average form. Both of them are equally valid. And so recapping all of these things, number lines are great when we have a single point, or a single number. But often we're going to want to work with ordered pairs, and we use the coordinate plane to locate those. Each of the quadrants, the first, second, third, and fourth quadrants, which are numbered clockwise from the top right, or not clockwise, counterclockwise from the top right, they each have properties about whether the x-coordinate is positive or negative, and their y value is positive or negative. While finding distance on a number line is as simple as subtracting the 2 points, we have to use the Pythagorean theorem, which then gives us our distance formula. And so you can either always draw 2 points and apply the Pythagorean theorem, or you can use the distance formula directly. And now we have to remember that when we take the square root, typically speaking, we get a positive or a negative value, but by convention, distance is always positive. So in our distance formula, we only ever care about the positive square root. And then, just like we had a distance formula, we had a midpoint formula, which gives us that point in between 2 points. We can either think of it as our point plus half of the distance between them, or the average of the 2 points. And that concludes 2.1. Thanks, everyone.